Hello guys, welcome back to our lecture 15. We're gonna continue our discussion about zener diodes. So now the most interesting part of zener diodes, which is basically, our continuation or our, development of the rectifiers, the diode rectifiers, basically converting AC to DC. Okay, so this is the most important application for zeners. Okay, or one of the most important applications in voltage regulators. So zener is here. Okay, and the sketch that you can see here is basically what we have discussed so far. Okay, we know why we need transformers to step down the voltage, because usually the input voltage is really high. Okay, or to control it, basically, the rectifier, we studied, half wave rectifier. We studied also the full wave rectifier in two versions, center tape and the bridge. Okay, then the filter is basically the capacitor. We said that we can improve the full wave rectifier or half wave rectifier by adding a capacitor parallel to the load, and this capacitor is called filter capacitor, smoothing capacitor, or peak capacitor. Okay, and now this is the last step, which is basically the regulation. This will convert the ripples. So the output here is something like this. It's ripples. It's not perfect DC. So the output here should be something like this. Just constant, just DC, perfect DC. Very, very close to perfect, basically. Okay. And here is, the discussions that we discussed. So the input is AC either before or after the transformer. The transformer just step up or step down the voltage. It doesn't change the shape, basically. So the AC will stay AC. The sine wave will stay sine wave. Okay. Then the full wave rectifier, for example, will it change that input AC into rectified voltage in direction. I mean, the direction is always positive, always, for example, like this. Then the capacitor will create these ripples, which is basically enhancement. So look at the variation here and the variation in here. There is a lot of variations. Okay, and the DC here is the DC in that stage is greater than the DC in that stage. Okay, because the variation is less, basically. Okay, and now look what the zener can do for us. Okay, it will make it perfect, almost perfect DC. And here is an example, so here is basically the input, which should be like this. This is, by the way, the bridge rectifier, bridge for wave rectifier. So this is basically a symbol for it. Without the capacitor, the output here is like this. Just what we see here. Then this capacitor will convert that output into something like this. And we're gonna see now this zener will make this output is even more or more DC, more like DC. And this is basically the load, just like a resistor, for example. Okay, so let's see an example, and from that example we're gonna understand well how the zener can really convert this into perfect DC. Okay, so in this example we have just the same circuit that we solved in the previous video, exactly the same. Also, the input here is a little bit weird. So the input here is a sine wave, but we didn't see such sine wave before. So if we go back here to the sine waves that we have, this sine wave is varying around 0. So this is basically, a sine wave, and this is, the time axis. So it's varying around. This is, for example, Vm, and this is minus Vm. There is, positive half cycle, there is negative half cycle. But if we look here, no, this sine wave is basically varying around some DC. It's shifted from the time axis. This shift is basically 60. If we're gonna write an equation for this sine wave, it will be something like this: 60 plus this peak, which is just 5. 65 minus 60 is 5. 5 sine omega t. Remember, the maximum of the sine is 1. So this will be 60 plus 5, which is 65. And the minimum is minus 1. So 60 minus 5 will be 55. Okay. This one here is basically Vmax sine omega t. Okay, 0 plus Vmax sine omega t. That's why you have Vmax and minus Vmax. Okay. Good. The first step, okay, is to determine. Good. So now, what is basically this sine wave? Just look at the, the DC shift here and the maximum of the sine. So 60 is much larger than 5. It's actually bigger than or greater than 10 times 5. Okay. So the variation is small, right? So that's basically the ripples. So these ripples here is basically, approximated using such, such model. A sine wave just, varying around some big DC. So this is basically ripples, model for the ripples. Okay, good. So basically that input here represent the output after the capacitor, after the filtering capacitor, the ripples basically. So let's see how the zener will behave in such a circuit. How the zener can convert such, still varying output, okay, of the input here, I'm sorry, to a perfect DC. Okay, the first step is to find, if the diode is forward or reverse, just like what we have done in the previous example. So you may say here that since the input is varying, so might be in the positive half cycle the diode is reverse, and the negative half cycle the diode is forward. And that's basically very wrong, because basically here you don't have positive and negative half cycle. You don't have negative, basically. Okay, because everything here is positive. Just look at here is, what you think is negative half cycle. No, it's not negative. Look, all the values from 60, minimum 55, which is still positive, then 60 again. So everything here is positive. So you can just think about this input as a battery like this, that you can change it. But basically the polarity is constant all the time, positive here, negative here. Okay. Now, what is the polarity? What is the connection of this diode? Is it reverse or forward? So this, battery, you want to inject the current in that direction. This current will go through R1. Then it's gonna, go in two branches here. So the positive current in the diode should go from N to B, which is basically reverse. That means reverse. Okay, because no positive current can flow in that direction. Okay, in forward, of course, but in reverse, yes. Okay, good. So basically, the diode is reverse. So the diode is reverse. The zener is reverse here. Okay. Now, if it's in reverse and this is a diode, it might, go into breakdown or on, basically. So to determine what is the voltage that we need to turn this diode into breakdown, we need the minimum input that we can enter to this circuit that will turn this diode into breakdown. So we need the input minimum. What is the input minimum? The minimum input, minimum Vn, basically, that turn the diode into breakdown. So let's calculate it. So at the input equal to Vn minimum, the diode is breakdown. So basically, Vd is equal to minus Vz minus 10, because Vz is 10 here. Okay, and ID at that particular moment is 0. This is a transition point. The diode, just review our last recording, the diode will start to become, on. So still, it's going out of the reverse, which the reverse off, so the current was 0. Good. So if we look at here, okay, from that, for example, from that, loop, we know that Vd plus Vo is equal to 0. So by KVL, Vd plus Vo is equal to 0. So Vo is equal to minus VD. So it's equal to plus 10 because basically VD is minus 10. And let's assume the current that is flowing in R2 is I2. So based on that, I2 equal to VO, which is the voltage of the resistor R2 over R2. So equal to 10 divided by 5, so it's 5 kilo ohms. This will give you 2 milliamperes. And since ID is 0, ID is flowing in that direction, this is ID. And we know that this, if we call this I1, so I1 plus ID equal to I2. So ID is 0, so from that I1 is equal to I2, equal to 2 milliamperes. So this is basically also I1. So I1 is equal to 2 milliamperes. Now we can make Kirchhoff in that bigger loop here. So the input from this big loop is equal to I1 R1 plus I2 R2. I1 is 2 milliamperes, R1 is 20. I2 R2 is basically VO, it's just 10. You don't need to calculate it again. 2 multiplied by 5, it's 10, which is just VO. So this will give you how much? 2 plus 20 is basically 40. 40 plus 10 is 50. Good. Now compare that, the input minimum here. Okay, the minimum input, that will turn the diode into brick with the minimum point here. It's 55, right? So basically, the current V input has minimum value equal to 55, which is basically greater than 50. I'm sorry, less. So this will be greater than 55. So basically, the diode will be on at that point when V input is equal to 55. It will be on when the diode is equal to V input is equal to 60. It will be on when the V input is equal to 65, and so on. So the diode will be on reverse, of course, breakdown all the time. So the diode, that means the diode will be breakdown all the time. Since it's in all the time it's a breakdown, so all the time VD will be equal to minus 10. So all the time VO will be equal to 10 volt constant. Now let's draw VO. So let's assume this is a 10. So VO is just a 10 like this, which is perfect DC. Okay, and that's how the regulator work. Okay, also this is just a simplification. It's not that that easy. Because we can't basically connect directly, the output of the rectifier to the zener like this. We need something. We need what's called a buffer. We need to put, for example, op amp or something. Okay, but that's the basic idea. Okay, that's beyond our discussion. This kind of buffer, why we need this buffer and stuff. Okay, so but basically, as I said, this is the basic idea, how we convert this, this input that is still varying, still have ripples, have variations into a perfect DC like this. Thank you very much, guys, for watching this video, and see you in the next video. Bye-bye.